Okay, good afternoon, everybody. So welcome back to those who have been with us for the last 2.5 days, and hello for those who are just joining us right now. So my name is Olga Vitek. I am a faculty in the College of Computer and Information Sciences here at Northeastern University. I'm one of the co-organizers, and I'm really glad to have a chance to spend these 2 weeks with so many of you. So before we start, we just have a little bit of logistics. So most importantly, we have the Wi-Fi here so that you are connected. We have the URL over there is for the slides. This is where the slides of all the presentations are located. I hope you are all on Piazza. How many of you are on Piazza? Everybody's. I should maybe ask who is not on Piazza. You are not on Piazza? Okay, so have you received the invitation?
Yeah.
Yes?
I'll work with the Red Sox fans down front.
Okay, so you work with Nat to get on Piazza because we have all the announcements and all the links and everything that comes through that. Okay, and so we will have some of our teaching assistants who will be working kind of between the rows to make sure that we have our setup for the next session. So let me go ahead and start. So we're now shifting gears. We are changing our topic from what we discussed in the last 2.5 days. So we will be talking now about the statistical methods for design and analysis of quantitative mass spectrometry-based proteomic experiments. And we will do many things. But before we even start talking about technical details, let's first talk about why we need to spend so many days talking about statistics in this area. And the reason for this is in quantitative mass spectrometry-based proteomics, variation and uncertainty are unavoidable parts of our experiments. So, and I hope that by now you have heard already from different programs where you were that the technical variation and the different types of variation come from many sources. So first of all, technical variation comes from the way how we store and handle and process the actual biological material. So the actual biological samples, the way they're stored will affect the abundances of proteins and our ability to quantify that. Then, of course, there is the instrumental variation. So once we have the biological mixtures, we need to analyze them on mass spectrometry. And we have secondary effects such as matrix and ion suppression, which will also affect the readouts which come from the instruments. Then also, it turns out that the tools which are used to process this data, such as Skyline or OpenMS or any other tool that you may use, they also make decisions which affect the quantitative readouts. So they have to locate the peaks, identify the peaks, quantify the peaks, normalize, and so on. And this also affects our ability to detect, for example, changes in protein abundance between conditions. And all of that can be optimized to some extent. So we can be very careful in how we process and handle the samples. We can be very careful in how we conduct the experiments. We can be, as informed as we can be in processing this data, but this is not enough. Because, actually, I had a collaborator who told me once that if our instruments are really good and our workflows are really good, then we don't need statistics anymore. And I would like to differ, and the reason for that is it's not like I'm disagreeing that we can really have good instruments and have really good workflows, but the main reason why we need statistics is because we're studying living systems. We're studying the biological organisms which themselves have natural variation in protein abundance. There is a variation of protein abundance from one person to another. There's also variation of protein abundance within the same person from one day to another, or from one developmental stage to another. And so the goal for us, if we want to do relative quantification, if we want to know what changes are induced by stresses, conditions, diseases, and whatnot, we need to be able to distinguish the systematic change which was induced by our stress from the artifacts of random variation, which come either from the biological reasons or from the technological reasons. And the whole kind of point of these 2.5 days and also of the next 2.5 days is really that. how can we distinguish random variation from the systematic changes in abundance which are induced by the stresses or conditions we're interested in. And so the reason why we need to be really careful with distinguishing the systematic signals from random variation is not because I say so. It's not because, statisticians say we need to do it, but because our final objective in all of that is to do objective and reproducible research. We need to make sure that our experiments can be repeated and reproduced later on so that our results actually are something that we can rely on in a future study. And so when we think about reproducibility, I would actually like to comment that reproducibility, it's not a thing. It's not something that we can do once for all, but it's actually a spectrum. So a spectrum of reproducibility goes from on one side where the results are essentially right only, they're publication only, and nobody can and nobody can even repeat this at all just based from the description in the publication. This is not what we want, obviously, right? We want something else. So the first lowest standard for reproducibility is actually repeatability. So if somebody did an analysis of a data set and obtained some results, we should be able to repeat exactly every single step which was used and get the same numbers back. So if we cannot repeat things exactly, and if we cannot get exactly the same numbers back, then we have a problem because we don't know how much of this result is actually corresponding to the stress that we're interested in. Now, at the same time, and you have seen this already when you talked about OpenMS or Skyline, there are many tuning parameters in all of these analysis steps which have to be there, are really important, but they're not really critical in terms of the biological conclusions that we want to obtain. And so when our results depend too much on the tuning parameters, it's actually a problem, right? Because we want our results to reflect biology and not the tuning parameters that we have. So the second layer of reproducibility is different from repeatability in that if we use multiple different tools or multiple different options which are equally reasonable for this problem, we will not have exactly the same numbers back, but qualitatively we should have the same type of conclusions. If our conclusions depend too much on the tool or on the parameter that we choose, then this is not really reflecting the biology. So this is number two. But this is not the whole story, because now what we really want to do is to not work with the same biological samples, but show that our results hold for new individuals from the same conditions or the same populations. And so the repeatable experiment is if we take the same samples and repeat the same mass spectrometry analysis on them, but the gold standard for reproducibility is to actually take new biological material, let's say new subjects from the same disease and new subjects from the same healthy reference group and obtain the same qualitative results. And so this is really what we are aiming for here. So when I talk about reproducible research, we want to do this, but to do this, we need to make sure that the entire spectrum can actually be carried out. And I would like to argue that statisticians contribute to the entire spectrum of reproducibility. So we contribute to this by developing statistical software which provides documentable and automatable reanalysis workflow, which is fully transparent. So first of all, you can rerun it, but second, you actually can see what's in there, and you can criticize this, you can disagree with this, or you can kind of figure it out. The second thing is data analysis. So we want to make sure that our conclusions are as little dependent on data processing tools as possible. And we also want to make sure that statistical models can handle variation. And then the last part, and this is really crucial, is the experimental design. Because even if our data are collected well and maybe analyzed in a way which is open and transparent and so on, if the experimental design was done incorrectly, there's no way in the world that, there's no statistical sophistication that can essentially compensate for the poor experimental design. And this includes, on the biological side, but also on the technological side, assay characterization, system suitability, and of course, the choice of replicates and so on. And so in this 2.5 days and in the following 2.5 days, we will spend a lot of time talking about all of these issues. So what I'm doing now is just a preview. Okay? So that's the idea. So before I move on, so do you have any questions? I realize that some of you are still working out some R issues. So let's give them a couple of minutes to work out the R issues and maybe see if you have any questions or comments so far on anything. It's okay? No questions? Okay. So then let me move on to what I actually would like to do in this next hour and a half. So there are 3 topics I would really like to address. And the first of them is the motivation of why we feel that we need to talk about statistics and data processing and reproducible research, specifically for mass spectrometry and proteomics. So this is a study which our group was involved in. And in fact, Mina, who is here, she did a lot of work as part of this study. So this study was organized by the Association of Biomedical Resource Facilities. I hope that many of you are familiar with that. So ABRF is an organization which brings together people who work in core facilities in different areas. And so their goal is not necessarily to do, novel, latest and greatest cutting edge research. Their goal is to analyze biological samples using well-established protocols and make sure that they do a good job using protocols which are well known. And so what they would like to do is to make sure that their workflows are well benchmarked and they perform really well. So what they do for that, they create opportunities for different members of core facilities to analyze the same data. And they analyze this using their own methods of choice, anything that they want to use. They don't know what the true answer is, and then they compare the results. And it is not a competition. It's more like comparing different practices and deciding what would be a good practice in this area. So this particular study was specifically focusing on statistical methods. So they were not focusing on mass spectrometry, but more like what happens once you have mass spectrometric data. So it was focusing on detecting changes in protein abundance between conditions. And to make sure that we can kind of evaluate different practices, we need some setting where we know the truth, right? Where we know what the right answer is. And so for that reason, the organizers, and I was one of the organizers, we created a data set which is a collection of 4 controlled mixtures. So these controlled mixtures have a tryptic digest of yeast. And in this digest, we had these proteins which were spiked in this tryptic digest of yeast background in varying concentrations. And so these are the relative concentrations in some units. So these are different proteins which were spiked in. And so you see that between mixture 1 and 2, 2 and 3, 3 and 4, this protein, for example, changes in abundance quite a bit. And then they added 2 more proteins which would had some additional concentrations. And so the idea was this. OK, let's have these biological samples. We will analyze them like this. So we had, these are some details. So using essentially a thermo instrument, LCMS, label-free using MS1 quantification, DDA, right? So there's some technical details on that. And then we also did a analysis where we identified MSMS spectra and we quantified MS1 peaks with Skyline. So we have a data set which was processed in one of the labs of the organizers. And we had raw data. We had the results of database search. So this was 5,700 proteins and so on. And then we also had MS1 quantification with Skyline. And so now the participants were given this data without this important information. So what we didn't give to them is the identity of these proteins. So these proteins were, we made fake IDs for these proteins so that they look like yeast proteins, so that they would not know. And the goal of the study was to take as input anything that they wanted. If they prefer working with raw data, just take raw data, use your entire pipeline. If you prefer having the ID but not quant, you can only take the IDs. If you prefer using all of that and just read this into R, so essentially Skyline reports, read it into R, and then you can just do statistics on that, and this is just fine. So that was the idea. And then, yes, please.
Sorry, so if you say 5 or 7 features per protein, you mean peptides?
OK, yeah, so we will talk about this in detail. It's peptide ions. So it's essentially a unique retention time and M/Z combination in the LCMS space. It's kind of like OpenMS defines features, right? Except that these are aligned features, right? So these are the features which were obtained across multiple runs. So I'm not sure if I said it was 4 replicates per sample, right? So let's see, 4 or 3. So suddenly I am 3, right? So, and however, you could have missing values, right? So it's not like you had to have a feature present in every run, but if it's present in some run, so whatever essentially your workflow is, you would work with that. OK. So yeah, 3 technical replics. Here we go. So 12 runs total. And let me just give you a preview. One of the reasons why I'm talking about this is to motivate the need for statistical analysis, but also because your hands-on parts will be working with this data. So you will actually get to see some of this data in the following hour. So, OK. And then, so this data excluded the IDs of the spiked proteins, but besides that, everything was available. And we had participants in the studies. So here from continents, somehow many came from Europe. And not as many came from the US. Most work in core facilities, but there were also some people who are doing research. The majority were bioinformaticians, but we also had some statisticians, software developers, and so on. And the majority actually were quite experienced, so they had 10 plus years of work in these facilities. OK, and so then once they did the analysis, they had to submit a form where they had to fill in first of all, the different steps of processing that they chose to use for this data. And then we asked them to report fold changes between conditions for each protein and tell us which proteins they claim are systematically changing between conditions and which ones do not change between conditions. So that was their task. So this is the result. So here we have on the, and by the way, this was double-blinded, so we don't know who participants are, and they didn't know who we are, so we didn't, hopefully it was not biased by that. So here the x-axis is the ID of the study. And different panels here, they separate submissions which were using MS1 quantification, using quantification by counting MS-MS spectra. This is some kind of hybrid approaches which used both, and these people didn't document what they did. Now, the color of the bar is their input that they used. So the yellow peaks used the raw data, so raw spectra. They didn't use any of our analysis. They just used the data as it's coming in. The light orange used peptide IDs, but not MS1 quant. And then the dark color used all of our data, which we analyzed. So they just did kind of the downstream statistical analysis on that. And you see that this horizontal line is the number of proteins which we provided as part of our analysis. So the first thing you see here is that the number of proteins reported by different studies was quite different. By the way, those guys misunderstood the instructions. They only reported differentially abundant proteins, right? Talking about reproducibility right there, right? So even understanding the instructions is not obvious, right? OK, but there's quite a bit of variation even in the number of proteins which the participants reported. OK. But that was not our objective. What we really were interested in is detection of differentially abundant proteins. So here is another plot. So again, each panel kind of separates intensity-based quantification, spectral counting, and hybrid. The x-axis is the ID of the study participants. Now, above the horizontal line, there's this black horizontal line here. The y-axis, let's see, below the horizontal line, these are the true positives. So we have 4 choose 2 possible pairwise comparisons between conditions. We know how many proteins we spiked in, so we know that the maximum number of true positive changes is 36. And so here, below the horizontal line, these are the true positives which were reported by the participants, because we just cross-matched their submissions to what we know about these proteins. Well, most importantly, above the horizontal line, these are the false positives. So there is quite a bit of difference between these submissions, which had some false positives, but mostly true positives, and these submissions, which had a tremendous amount of false positives. So this one, I don't know if you can read. They reported 2,000 differentially abundant proteins here, right? And this reported 700, right, and so on. Now, notice also that it doesn't matter if you do intensity-based or spectral counting or hybrid, you have these discrepancies, right? And it doesn't matter if you start with raw data or with partly processed data. You would have these discrepancies as well. So clearly, there's a lot of variation on it. And again, remember, no different mass spectrometry, same raw data, right? Same files coming out of the instrument, only the statistics, right? Well, and identification, quantification, right? So that introduces all of this variability. Okay, so we also asked the participants to report fold changes between conditions. So here we have study ID, and the study ID is in the same order as in the previous slide. And here the y-axis is the log fold change only among the background proteins. And this is the log fold change reported by the participants. So on the log scale, the fold change is supposed to be 0, right? And so here's the absolute value. So it has to be as close to 0 as possible. So see what is interesting here, right? So these log fold changes, all of them had potentially some large values. So every single study had exposure to some really large log fold changes. However, the studies here, they could distinguish these big changes from systematic changes, right? So they were not really, intimidated by big fold changes. They said, okay, these are not true systematic signals. These are just artifacts of random variation. But this group of submissions, they were misled by these changes, and they claimed that these are true changes in abundance. And so the goal of what we need to discuss in these 2.5 days and also in the next week is how do we go about distinguishing true changes from these artifacts. Well, so that was a really important lesson for us, right? So, well, what happens next? So we try to actually parse the forms where the participants described exactly what they did to arrive to these conclusions. And we try to kind of make it systematic. So here we talked about the input, same color, right? So raw versus IDs versus peak intensities. Now here we said, okay, what do you use for identification, skyline, max quant, progenesis, and so on? What do you use for quant, feature intensity, spectral counting, and so on? What do you use for summarization at the protein level, peptide level? What do you do for statistics? So there is Perseus, Excel, R, whatever you use, right? How you make conclusions. This was multiple testing. So, personally, I find that it's very hard to find any patterns here. My point is that in this figure, there are many colors. So there are very many ways to go about that. So it is not like, there's 2 or 3 workflows that people used, but very clearly different people used very different workflows to essentially go about the same problem, right? And I should say also that this was very difficult to classify because sometimes people say like in-house scripts, so what do you make of that, right? Or I use MATLAB, right? Well, it's like saying I use mass spectrometer. It's really not enough to say what actually happened, right? Or also what we noticed that sometimes people tried to answer the questions that we asked, but their answer didn't really match the question, which made us realize that maybe people didn't quite know what they were doing in detail, right? For example, they didn't know what this certain software was actually doing and how it corresponded to that particular question. So the biggest conclusion here was that there are many ways to go about this problem, right? And there are many different options. So the next thing is, so we decided to say, okay, let us at least classify the submissions in terms of, how reliable the conclusions are. So the metric that we used was positive predictive value. So positive predictive value is the proportion of true changes among the claimed changes. So if you overlook some true positives, fine, but at least you don't go in the wrong direction from what you detect, right? So how many of your detected changes are reliable leads, essentially, right, for that? And so here we see that this group of submissions, they have positive predictive value 70% or higher. So, okay, this is reasonably good. Here, percentage of true changes among the reported changes is between 0.2 and 0.7. I would say it's not great, but below 2, it's really, really bad, right? So this is bad. So that was the only thing we could use to separate the submissions. And so the next thing you can actually ask yourself is, okay, well, but can we at least say some things like, for example, did max quant do better than skyline? You know, or so this was really the question which everybody wanted to know, right? So is there the winning tool, you know, that we can just use and be done, right? Okay, so let's take a look at that. So here are multiple submissions, which all used MaxQuant and Perseus for statistical analysis, right? So this submission did clearly very well. These two submissions were in positive predictive value, kind of below the bar. Okay, this submission used Skyline and linear models in R. So this submission did very well. This submission did very poorly. Now, this submission, so participants could submit multiple things. So these groups compared peak intensity versus spectral count. This group found that peak intensity and spectral counts did equally well or reasonably well for this. Here, one group found that one did clearly much better than the other. So also in terms of the choice of the workflow in different groups, they arrived to different conclusions. So it's extremely, extremely variable. However, we found one very clear pattern. So here on the next slide, this column is, oops, do I see my, yes. This column here is the ID of the group who did the analysis. And what I'm doing here, I'm circling the submissions from the same group. And what you see this, with one exception, these circles never cross this line. So what it means that the labs who are expert and who know what they're doing, they can use multiple tools and they will do well. And the labs that need training, they can use multiple tools and it will not help. And so this is really the main reason why we realize that it's not about the tool, it's about the user. And how we how well we can use these tools, how much we understand what is actually going on, how much we know what are the right assumptions behind that. And this is why we're here, right? Because it is not enough to have a tool which you download, you know, or buy for a lot of money, right? It is really about how we understand what the tool is actually doing. So this is really the important part. So now as a preview of what we would like to so what we learned from that, and in fact, this study, it's a few years old, and it actually inspired, to some extent, the program that we do here at Northeastern. So what we would like to do, not quite in these 2.5 days, but on Monday through Wednesday next week, is to arrive to these plots, which are the type of a standard which we use to report the changes in abundance between conditions. So here, the x-axis will be the log-fold change, which we call practical significance. The y-axis is the negative log p-value adjusted for multiple testing, which is statistical significance. So essentially, the values above this dashed line, these are proteins which are statistically significantly differentially abundant, and the proteins below this line are do not have change in abundance above their variation. And so you see here that we can, with this type of plots, we can distinguish the spiked proteins, although sometimes we can have false positives as well. So this will be one type of thing that we will be doing. Then, well, we will not talk much about spectral counts here, but we will talk about different options of data processing. So what also happened as part of the study is, since the time we did the original analysis and provided this to participants, collected the results, and so on, Skyline evolved quite a bit. So we also reprocessed the data once again with the newer version of Skyline, and found that, well, things changed, right? So now we don't have exactly the same results. So this is important to keep in mind. And in particular, if we think of this log-fold change among the background proteins, so this was the old analysis, and this is the new analysis. So the improved peak quantification that Skyline had reduced the median log-fold change among the background proteins. So clearly, it reduced some of the artifacts which were present in the older version. So data processing matters. So this is to say that we will start from Skyline reports or OpenMS reports and so on, but the upstream steps are extremely important. And so then, yes, please.
Spectral counts here seem to have a bit of an edge over intensity.
Yeah, this is actually an artifact of spike in experiments. And the reason for this is the background is constant, right? The background doesn't have biological variation, it only has technological variation, right? And so, and the spectral counts have this compression of the fold changes because they're very discretized. And so the fold changes estimated from the spectral counts, they just don't have enough variation. So because the experiment doesn't have as much variation as we would have in a real biological study, and because the background proteins are very stable, and also because our fold changes are relatively large, spectral counts actually does quite well here. But it doesn't mean that it would do as well on a real biological study. And we can talk about this later. It's essentially because it's semi-quantitative, because especially at low abundance, you cannot really distinguish between 1 and 0, right, or 1 and 2 spectral counts. Okay, so this is to say that data processing matters. And what we will do, and this is for those of you who stay later on for the DIA part, for the very last part of the next week. So what we also realized that different choices of processing, of course, also affect detection of differential abundance. So what we could do is to think of different tuning parameters, which would use, for example, to filter different identifications of MSMS spectra. So here in this particular table, so we use proteins which have at least 2 PSMs, right? So at least 2 peptide ions mapped to this protein. We will take 3 isotopic peaks and sum them to quantify this particular feature. And then there are methods which would allow us to characterize the quality of identification of these PSMs. And so essentially having a Q-value cutoff of 0.05 means that it's very stringent. You would only allow few of these PSMs in your data set. This cutoff is very inclusive. You would allow all the IDs. And so we can see how this affects the number of true positives and false positives. And then we could repeat the same thing by looking at proteins quantifying only by single monoisotopic peak, or if we allow single hit wonders, and how it will affect our ability to detect differential abundance. So again, positive predictive value is the proportion of true changes among the claimed changes, and you see that these choices clearly affect the performance with the same statistical method that we have. So we will not have much time to do this before Wednesday next week, but if you are staying for the full 2 weeks, you will actually have an opportunity to investigate this to a greater extent and see how it propagates itself all the way to statistical conclusions. So this is our plan for the remaining week and a half. So now this particular study has been published. The data set is here, but you don't need to go here because you will have it as part of your hands-on. And if you want to know more, so you can look it up in this manuscript. So yeah, okay, any questions so far on that? I hope you have questions. Anybody? Yes?
What is the difference between data processing and signal processing in the previous 2 slides?
Specifically here?
This and the previous slide.
Oh, right. So these were different versions of Skyline. So Skyline, evolves constantly, right? And so they change their ways of, quantifying peaks, integrating peaks. There are many different, like distinguishing, like, noise, floor, and so on. Whereas here it is for a same version of Skyline, actually the most recent one. But now with that, we can make decisions. Okay, do we allow single hit IDs or not, right? Do we quantify a feature by monoisotopic peak or by the entire isotopic distribution? Or, if we want to use MSMS IDs for quantification, what is a good ID and what is a bad ID? So the score essentially tells you, okay, how good or bad IDs you require for a quantification. So all of that are tuning parameters. And when I was saying earlier in the hour that you have to have these parameters, you cannot not have them, but we also don't want our results to depend entirely on that. And so using this type of controlled mixtures is one way to kind of see what is reasonable and to have some guidelines, right? And then within these guidelines, you would hope that qualitatively the results will be very similar.
But do I understand correctly that if you do it like as a Niagara panel, that the exclusive versus inclusive approach actually doesn't really matter?
In this particular example, so we've worked a lot with spite mixtures like that. So there are many good things about them because you know the truth, you can kind of do many things. But in terms of the actual challenge, right, it's much easier here than it is in real biological studies. So I wouldn't take it as, now. So first of all, you would want to have multiple of those mixtures, but you also would want to work with biological studies. And in fact, on the last 2.5 days, we will not be working with that. We will be working with the actual biological data set with DIE, which will be processed in different ways. And for this data set, we have some sense of biology. So we will be using biological patterns to evaluate the performance of different processing, as opposed to, just the spiking. So this will be a lot more meaningful than what we do here. OK. And so, well, that's sometimes how people perceive this, right? So it looks like, at least from this study, that people could do, a lot of different things like that. We would like to get closer to that. Although it will not be possible to have one size fits all for every study, right? And this will be very important to remember. OK, so now, before we actually do, and in fact, the real statistics, we'll do it tomorrow, right? So today we won't even get to the actual analysis. So what I would like to talk about today is how to actually frame statistical questions and also talk about the experimental design. So this really is the plan for the hour. So let's talk about the scientific question first. So as I mentioned in the beginning, statisticians contribute in many ways, right? So we contribute in terms of data processing and so on. But I would like to argue that we also contribute upstream in terms of understanding what is the right experiment and also whether our measurement technology works as it should and so on, right? And so I have this little cloud for data acquisition, So usually it's a lot about the experimental parts, and you have a little statistics box. So I kind of have the opposite here. I have a lot of statistics everywhere and a little data acquisition box. But I hope you're with me on that. So let me focus on this part here first. And the reason for that is that we want to know how different questions that we may want to ask translate themselves into different experimental designs, and in turn translate themselves into different statistical analysis. Because before we even start doing statistics, we need to understand what is the right method for the right question, so that we actually direct our energy in the right place. So the kind of an easy way, at least the way I think about that, is I think about partitioning all the types of statistical questions into 3 broad themes or goals. And so the first statistical goal is class discovery. So what does it mean? It means that we have a data. Maybe this would be the easiest for us to think about. You all have seen this. So here we will have the rows would be analytes, let's say proteins somehow, or peptides, or whatever you would have in mind. The columns are biological samples. And the colors correspond to the abundance of this analyte in this biological sample. So class discovery means I want to find analytes which have similar patterns. So this can be, I want to find proteins which have similar patterns in the space of the samples. This is important because maybe these are co-regulated proteins, right? Or maybe these are proteins which are part of the same response mechanism to whatever stress was induced. Or it is also meaningful to look for samples which are similar in the space of the proteins, because maybe these are disease subtypes, or maybe there's some kind of other shared properties of the subjects. So the important thing is that we don't really know what our class is. We don't know what disease subtypes are, right? We don't know what the mechanism is for the stress response. We're just saying, OK, here's my matrix of the data. Go and find something which is similar. So the problem with these methods is that we can find things that are similar for wrong reasons, right? They can be similar because we have batch effects, or because we process things on different days, or because we had an instrument failure, right? And so on. So these methods do not have a sense of what's useful and what's noise. And they will find things which can be similar, not for reasons that we're interested in. And the type of methods people use here will be principal component analysis. I'm sure you have seen that, right? So here the axes are linear combinations of proteins. Each point is a sample. We would say points are together. Therefore, the samples are similar, but maybe they're similar because they were processed by the same person, right? And not because they have the same disease. Or we can look kind of for clusters and look for the same profiles. So this is really great for data visualization. This is certainly great for QC. one way I would like to use principal component analysis is to look for failed samples. If you have a sample which is compromised, it will kind of stay outside of the bulk of the data. This is a really good way of detecting that. But a typical mistake that I see a lot in publication, when I review papers that are submitted to the journals, will say, we have principal component analysis plot and all the disease cluster together and all the healthy cluster together. Therefore, I found a biomarker of disease. Principal component analysis does not do biomarkers. And the reason for this is it doesn't know what a disease is, because we never gave an information about the disease to the method. All we gave to this is samples which are together in the matrix. That's all. So this would not allow us to have error rates, for example, will not allow us to help make this clinical decisions or anything like that. So this is really best to look for visualization or QC, but this is it. And this is a part of an unsupervised method, and it's unsupervised because we do not provide the information of what's interesting to us. We just say, go and find something. So it finds something, right? But it may not be what we want. Yeah, and so this was just some examples. If we want to kind of, there is this website with random correlations. There are plenty. You can generate tons of them, right? So here's the divorce rate in Maine correlates with per capita consumption of margarine, right? You can find all kinds of things, right? But things which correlate, don't. But here we laugh, right? But when we see a plot like that, we're like, huh, right? That's interesting, right? So we have to be careful with that. So the second statistical goal, this is already a supervised method, because now we're saying, okay, and by the way, I will talk about healthy and disease just because it's easy. You can kind of map it to your kind of study of interest, right? So let's say we have healthy and disease subjects, and now we'll tell the method, this is the group which is labeled as healthy. This is another group which is labeled as disease. And what we would like to do is to see if for this particular protein, so this will be the log abundances, maybe for this peptide of the protein or of the summarized values of the protein and somehow. And we want to know if this protein is changing in abundance between healthy and disease systematically, or is this change consistent with the random variation between the groups. So the methods you would use for this will be t-test, will be analysis of variance. There are many kind of things like that. The readouts of that will be p-value, posterior probability, and so on. So this is very useful. But again, a mistake that I see a lot is that people say, okay, I have a protein with a small p-value. Therefore, I found a biomarker of disease. It is not a biomarker of disease. Small p-values are not really related to biomarkers. And the reason for this is the following. So this is a little bit more subtle than the previous case. So the reason for this is this. So when we think about biomarkers of disease, what does it mean? It means that a biomarker is supposed to be actionable, right? So a doctor has to be able to make a decision for this particular patient based on this readout, right? So here, this particular goal, we want to compare the averages between two populations. The doctor does not see an average patient. The doctor sees a specific patient. And maybe on average there is a change, but it is not actionable for the clinician. So we want to be able to act on the individual basis and not on the average basis. And so just to illustrate this, here's an example. So let's say we have healthy and disease. So here, clearly, the change between two groups is larger than the variation within each condition. So probably it is systematic, right? But in this particular example, the change can be an artifact of random variation. However, if we have a large enough sample size, we can be really, really confident in this mean, and we can be really, really confident in this mean. There are some statistical techniques which tell you, okay, this change is unlikely to be an artifact because we have so much data. So this type of change will have a small p-value, but then when this patient comes to a doctor and has this abundance of the protein, is it healthy or disease? You would not know. So a p-value compares averages, and averages are not, p-value is a result of comparing averages, and averages are not actionable. And by the way, the same goes the other way around. So we can actually have proteins with large p-values, meaning not differentially abundant, but they can be quite actionable as biomarkers. So here is an example. So we have two proteins, 1 and 2. Let's say blue are healthy subjects, red are disease subjects. So here, clearly, protein has difference in abundance. And so this would be differentially abundant protein and predictive protein. But here, you can see that protein 1, among the healthy subjects, it spans the entire range of abundance. And then among the disease subjects, it also spans the entire range of abundance. So you would not find difference in abundance for this protein. The same for protein 2. You will not find difference in abundance between two groups. But as a panel of two proteins, they're perfectly predictive. So this will be proteins which would not have small p-values, but they will be perfectly actionable in a clinic. So the reason why I'm saying that is I hope that you see now that if we're interested in comparison of averages, we will be using different methods than if we're interested in making actionable statements for individual patients. And this would allow us to design experiments differently. So for these 2 weeks, we're actually focusing on this goal too, because this is the most common goal. And usually we would do this in proteomics. We would do this as part of screening or initial kind of discovery experiments, because proteins which are differentially abundant may be good candidates for predictive proteins and good leads for follow-up, for example, with targeted methods like we discussed just before with Skyline, right, and so on. But these are by no means conclusive statements if we want to do biomarker discovery. And so the last goal would be, okay, well, let's kind of do that as well. So it is very easy to kind of extrapolate from averages to individual people, right? But sometimes we go wrong, right? So here, number of husbands. So yesterday was 0, today is 1. If we keep going, we will have very many husbands soon, right? So, so we have to be very careful from averages to making individual conclusions. Okay. But so for statistical goal 3, this is the right goal if we want to make actionable conclusions for individual subjects. So this is also a supervised class of methods, because now we need to annotate every subject if it's healthy or disease. And these methods will be going like that. So for example, here we have 2 proteins. Blue are healthy, red are disease subjects. So the methods are machine learning methods, which will be developing classification techniques that distinguish healthy from disease. So for example, this machine learning method ignores protein 1, and it says if protein 2 is large, it's healthy. If protein 2 is small, low abundance, it's disease. And it's all right, but clearly we have some mistakes here. So now a better algorithm would use both proteins and have some kind of nonlinear rule. It has fewer mistakes. And then another method will be very, very specific here and will contour every single sample. So clearly this one probably accommodates too well some random artifacts which we have in the measurements here, right, or in sample storage and whatnot. This one is probably too simplistic. And so these methods will go about finding the middle ground and finding methods which are complex enough but not too complex to make these predictions. So that's the idea. And so this is what you would need for biomarker discovery, and the readouts would be misclassification error, sensitivity, specificity, positive predictive value, and so on. So this is what you would be reporting if you really want to kind of have this type of conclusions. Okay, but again, these methods are also not the end all. So this, well, if you have heard of deep learning, so deep learning will be one class of these methods, right? And our unique justified feature uses deep learning to find data that agrees with your point of view. You can also find that, and so this will be this type of situations where we essentially accommodate our data just to show what we want. Okay, so let me take a little pause here and see if you have any questions. Please.
The number of samples you have is also significant.
Say this again.
So the number of samples you are working with, is that an effect also in analysis?
Most definitely. Most definitely. The sample size is very important. However, the only way for you to really know what's the right sample size is when you know how you're going to analyze this data and how you're going to actually work with this data. For that reason, I'm actually leaving the sample size discussion for the very end on Friday. We will certainly talk about this, but we have to talk about everything else first. But obviously, sample size will have a big effect on that. Well, yes. So more samples are always better, right? However, at some point you get diminishing returns, right? And at some point you can establish your evidence with some number of replicates, right? And then everything else will be just confirming what you want. And a big part of what we do here is to figure out what's reasonable enough, right?
Yeah, I feel if you have more sample, actually, even you have a very low fold change, you can still get a very significant p-value. So then, it's hard to, then how do you judge this?
Exactly. So you're actually touching upon something really important, because you can show, and we will talk about this tomorrow, you can show that the p-value is a function of the sample size. And you can always show anything as significant just with enough replicates. And this sometimes happens, when people absolutely and totally want to show something significant, they will just collect, large enough number of replicates. And p-value is a deterministic function of the sample size, right, for that data. So what does it mean, right? Well, first of all, clearly more replicates is more expensive. So you want to optimize experimental design as function of costs and feasibility. And a lot of the sample size calculation would be to say, okay, also you mentioned small fold change. So what is the smallest fold change which is actually practically significant, or practically useful for me, right? So maybe a fold change of 1.1 is not really that useful. But maybe in other situations, 1.1 is exactly what you're looking for, right? Depending on the biology. And so you would decide what is the minimal fold change which would be interesting to you. And then you would say what would be the sample size that is needed to actually be able to distinguish this change from the artifacts of random variation. And the important part of experimental design, and we'll talk about this right now, is that what statisticians can do, we can help you allocate the resources to optimize the use of your limited number of samples, and be able to be more effective in distinguishing random variation from systematic variation, even with less replicates. And I will show you how exactly in a minute. So at the same time, especially when you work with human samples, the sample size that you would need is typically larger than most of the studies do. In my experience, the vast majority of proteomic studies are underpowered, meaning that they don't have enough replicates for that. But I can also see that there is a kind of the opposite thing, where if you have a controlled experimental system, limited variation, you don't have to spend money to collect infinite replicates. A certain number of replicates will be enough. And the way to do this, and as a preview, is to have a pilot study where you would understand how much variation there is between conditions, how much biological and technological variation you have in your system, and you would use this pilot study to design the actual experiment which has the adequate sample size. So that would be the way to do it. Mm-hmm.
And then does it mean still that it's possible to use biomarkers?
It may mean anything. So all you're saying is that they have different location on this plot. These are not biomarkers, and they can cluster for wrong reasons, right? Or maybe they have different abundances on average, but for the individual subjects, you will not be able to actually decide if the individual subject is healthy or diseased. These methods are fundamentally not designed for biomarker study.
If there are possible interesting or differential changing ones, is there a way the ones that are not differential changing and then to see again as a correlation? It's not a biomarker.
Well, this is, let's see. My favorite quote these days is the inverse Marie Kondo principle. You're not allowed to throw away data that don't spark joy. So we can't, right? So let us come back to this a little bit later, right? And we will see how we can actually work with that. Yes?
I have some global question, maybe even philosophical, to understanding of all biomarker research. Let's say you have a healthy group and you have disease group, and you follow the set of proteins which are differently they are biomarkers for this disease, but they are not, because maybe it could be a general inflammation or
Exactly.
whatever. How to design a global study, because you cannot take all possible disease in account, right, in one study. You cannot compare with the rest. How do you do it? How you are confident that you are
So you're talking about specificity, right? So how specific the markers are, and we see this a lot. For example, inflammation, right? It's very common, right? So everywhere. To be honest, I don't have a good answer to that. So what you want to, because you can say that this is predictive of that, right? But you cannot. How can you say this is not predictive of everything else in the world, right? So this is very hard. So I think what people do, they are looking for other types of conditions and diseases that are most likely, to be confounded with the disease you're looking at, and designing studies to specifically see.
But then it's another question arises how you compare your own data with data from someone else, because they're absolutely differently designed, varied and so on.
So you definitely don't want to compare this nominally, right? So what you can do, that's a whole different discussion. You know what? Let me talk about the design, and then we'll see how much time we have. But essentially, the short answer to this is you need to have appropriate controls for every study and make sure you compare each of the diseases to its own control. And those comparisons, either on average or predictive, they are more comparable across studies than just nominally the abundance of proteins. Okay, but I will make sure that we'll talk a little bit more about that as well. Okay. So experimental design, let me talk a little bit about that. So let me, again, talk about healthy and disease, just because it's easy, but you can think of other contexts as well. And let's say we have two populations of subjects which are the same for all the practical purposes, meaning that they have the same distribution of other diseases, age, gender, lifestyle, and whatever else can affect their protein abundances, except for the fact that this population is healthy and this population has the disease. So we just discussed earlier that we have two types of variation. So one is the biological variation, meaning we have different protein abundances from one person to another, and then we also have the technological variation due to the measurement of protein abundances. So since the populations are, for all practical purposes, infinite, we cannot investigate every single person in this population. What do? We take include in our study a random sample from the healthy subjects and from the diseased subjects. So this is our first layer of variation, because if we want to repeat the study, we'll have some other people, right? And if we have other people, we have other protein abundances. So this is the fact that we select random subjects in the study induces the first layer of variation. And then so we take, but again, the protein abundances in these selected subjects is still unknown. What we actually know is that we take the subjects and we profile them using mass spectrometry. So the only thing we actually see is the peak intensities that we collect here. And so now we have two layers of variation. One is the biological variation. So we have different abundances because we select different subjects. And then we also have the technological variation because we have some measurement artifacts from that. And so now what statisticians do, and this is what is called the process of statistical inference, is to take what is observed, so things that we can see, and make conclusions about what we want to know and which is unknown. So inference is use what we have and make conclusions about what we don't know and what we want to learn. And the inference has really two big dangers to it, right? So two ways that we can be wrong. It is bias and inefficiency. So bias means that we're systematically wrong. So it means that the difference, let's say, in protein abundance between healthy and disease readouts in our mass spectra is systematically different from the difference in the underlying populations. And then variance or inefficiency means that these differences are so noisy that we just cannot say anything meaningful about the underlying populations from that. And so the goal of statistical experimental design is to eliminate bias and variance and inefficiency. So let me restate the same thing, but now using some notation. I won't do much math, but I just want to introduce some notation here.
Yes. About the randomly select individuals, so if the patient, like the gender or the age
Yes. Hold that thought. I have a slide on that. So we will take a look. So yes. So for the experimental design for the moment, right, our big concern is to minimize bias and variance. Well, maybe I can answer this, comment on this already. So if you have protein abundance that is affected by age and gender, right, so it introduces more variation, right? So at the very least, it contributes to the inefficiency, right? Because now you have protein abundance that is variable for these reasons, right? But you can also have bias. Let's say all the healthy are male and all the disease are female. So now you will have a difference which is systematically different from the changes in the population because it's affected by male versus female, right? So we want to make sure that this doesn't happen. So in terms of kind of notation, what happens in my mind, you know, when a collaborator comes with a new study, this is actually how I think about this, is that there are these constants which are available or can exist in the population. So this is the mean abundance of the protein in the entire population of healthy. And this is the mean abundance of the protein in the entire population of disease. Now, we will never, ever, ever know what they are, but we assume they exist, right? And they're constant. And in statistics, the convention is that we use Greek letters for things which are not observed and not known. So we use mu to say that these are unknown quantities. Now, we select studies, include studies into our subjects into our study. And so now each subject also has their own individual protein abundances at this time point. And they're also unknown because we cannot see them yet. So now I also have a notation for them. These are the abundances of the protein of these subjects, which we also don't know. What we do know is the intensities of the peaks in the mass spectrum. And so those are in Latin letters because those are actually observed. And now the process of inference is to take what we observe, have some summaries which may be meaningful one way or another, and then use these summaries, make some assumptions about them, and make conclusions about the actual quantity of interest which we don't know. And then bias in this case means that this difference systematically deviates from this difference. And inefficiency means that we have very large variance associated with that. And this is how statisticians formalize this, and also this is how statisticians compare different experimental designs. So when you talk about how many replicates you need, what we will end up doing is saying, well, okay, what's the bias of this design, and what's the variance of this design, and how it affects our conclusions. So that's really how we will decide what we do. Okay, so we want to avoid bias and variance. So we can do this using 3 fundamental principles of experimental design. And these principles, I did not invent them. They exist like for over centuries. So Ronald Fisher, early 19th century, was at the origin of that. He worked a lot with agricultural experiments, and this had a lot of influence in how modern statistical research is conducted. And so the first fundamental principle of experimental design is replication. So I hope I don't need to convince you that we need replicates. But let's just kind of review why this is a good thing, right? So it allows us to do 2 things. It actually allows us to carry out the inference and understand how much noise and uncertainty we actually have in our process. And the other is it allows us to minimize inefficiencies, so be more confident in the individual means. So here, let's say we have 2 LCMS, label-free LCMS runs. This is from healthy and this is from disease. Let's say each protein is quantified just with 1 peak to keep it simple, right? And so now we're interested in comparing the peak intensity between healthy and disease. So we have 1 measurement for the healthy and 1 for the disease. So is it systematic or is it random variation? Anybody? What do you think? Exactly, who knows? There's absolutely no way to tell because we don't know what is the random variation in the system. Now, if we have replicates, we can distinguish these 2 situations, right? So here we see that the replicates are very tightly clustered around the mean. So this is unlikely to be a random artifact. Here it is much more likely to be a random artifact. Exactly the same difference between the groups. So, by the way, and I will mention this several times in the future, this is always on the log scale, right? So on the difference on the log scale is the log of the ratio, right? So log of the difference is essentially a log fold change, if you prefer think in terms of fold changes, right, between two conditions. So what we just said, that without the replicates, we don't know if this log fold change is a systematic or a random artifact, right? And the same thing here. So we need to have replicates to understand how much noise we have, or variation we have in the system. A consequence of that is that a fold change cutoff makes no sense whatsoever. Because this is exactly the same difference between conditions, right? So it's exactly the same log fold change. So applying the fold change cutoff doesn't incorporate the information on the variability within each group. So fold change cutoffs alone are not really meaningful. And I would like to argue that probably some of those participants who were misled by large variation, they were probably applying fold change cutoffs to detect differentially abundant proteins.
So fold change cutoffs, totally agree. Fold changes in general kill off your variation, and as a result, you end up having these like, sure, it looks super amazing, but the reality is very different. What's your recommendation how to best represent that kind of information in a lot of work in some sense? Do you present both? Do you present one? Is there a better?
We will spend 2.5 days this week and 2.5 days next week on that. So I hope that this will answer your question. And if it doesn't, well, we can have more discussion.
Okay.
Yeah. But the first message is don't use fold change cutoffs. So I think that's good.
Can be used in combination with a statistical significance?
Definitely. So if you have the statistical significance cutoff, nobody prevents you from saying, OK, if it's below a certain level, I'm not interested. So you choose what you follow up on, right? But you don't replace statistical significance with the fold change cutoff. Yeah. And by the way, these figures and this discussion is from this review, which we wrote quite some time ago, but I think it's still, so there's a lot more text that comes with that. OK, so the second fundamental principle of experimental design is randomization. So I hope you also know, but let's kind of review this again. So randomization is a really important tool to prevent bias, and prevent bias especially from sources that we are not aware of. So bias is the worst thing, actually, because bias is reproducible. So let's say we have females in the healthy group and males in the disease group. We'll have some difference between protein abundances. We will say, great, we found a difference, right? Let's repeat it again. Let's have another experiment where, again, we have males versus females. We will see again a big difference. Great, it's reproducible, right? But we're reproducibly wrong. So this is not what we're looking for, right? So randomization allows us to eliminate these artifacts, especially from sources that we are not aware of. Because if we randomly assign samples to treatments or to all the steps of processing and data acquisition, then whatever artifacts can happen, they will average themselves out across both healthy and disease, especially if we have enough sample size. This, by the way, can be one argument for a larger number of replicates, because you know that you may have many artifacts. You don't know where they come from. But so if you have larger sample size, you can kind of eliminate some of this variation. So let's take a look here. So I use day as a proxy of this type of artifact. So let's say for healthy subjects, we acquire the data on day 1 and day 2. And then for the disease subjects, we acquire the data on day 3 and day 4. So now we have a big difference between the two groups, but we have a perfect confounding, because now we cannot distinguish the change that is due to the disease from the change that is due to the day. And if I am to guess, it's due to the day, right? And it's not due to the disease. So because day is a proxy for many things, right? For the person, for the batch of the materials, for the temperature, for the instrument performance, right? So there are many things which can happen in time. So this is an example of essentially wasted resources here. On the other hand, if we randomly assign samples to days when we acquire the data, well, clearly they will have an impact on the protein abundance, but it will average itself out more or less across multiple groups. So we'll have more variability because day-to-day variation is part of it, but at least we don't have the bias. So it's not very efficient, but at least it's not biased. So this is one good way of doing this. And because I forgot to mention earlier, so here if we have two levels of randomness, biological and technical, we have two types of replicates, biological and technical replicates. And the same thing here, if we have two levels of randomness, we need to randomize both on biological replicates and on technical replicates. So we need to randomly select subjects in the study, and we need to randomize every single step of data acquisition. Just pick up. Yeah.
So usually, depending on your type of experiment and what access you have, sometimes the time of the mass spectrometer is limited. So I wonder whether from a statistical point it makes sense to include technical replicates, or is it the advice I've heard is like, don't waste your time on technical replicates, just include more biological replicates.
That's usually the right advice. So it depends. So it's more nuanced than that. But let's say you have one person, and you collect many technical replicates from this person. So you quantify this person really, really, really well, but it's still one person, right? So you still don't know how much person-to-person variation you have. So we will talk about this more formally at the end. The short answer is, if you have a limited number of runs, you will be much better off using them for different biological subjects, because you will cover the full extent of variation much better. But there are some, nuances there where technical replicates can be helpful. For example, if you need some references for locating peaks, and things like that. So for some certain things, especially when you develop the assay still, it may be useful just to kind of figure out how much technical variation you have. But once you have an assay which you have well under control, you know what you're doing, you will be much better off using every run for a new biological sample.
Following on that, if I'm not limited in measurement time, does it give me anything at all to add technical replicates?
If you really cannot have access to more biological samples, it will help marginally, but it will help more if instead you have different biological subjects. And we will actually show this formula as well on Friday, right? So you can actually write it as a formula. So, yeah. Okay, so this is for randomization, right? So and it is really important, especially from the sources that we're not aware of. And there are some examples here. This is an older paper, which I appreciate very much. These are statisticians from MD Anderson Cancer Research Center who work with clinical collaborators in their institution, analyzing their data. And they published a paper essentially showing, all the ways things can fail, right? They published all their failed analysis and kind of explaining what happened and what was wrong. So here's one example. It's an old technology, but doesn't matter. Same thing holds now. So it was a CELDI experiment, and they were studying 5 types of cancer. And the samples arrived to them anonymized, so they didn't know which sample corresponded to which subject. And they were in charge of doing goal 1, right? So unsupervised class discovery. And they did this clustering. So here, the x-axis are the samples, and the dendrograms linked together samples which are more similar to each other. And so they found that instead of 5 groups, they have 6 groups. And they were super excited. Maybe they found a new subtype of cancer that was part of that. But then what they also did at the same time, they made the plot where the x-axis is the same. So it's the same ID of the samples. But then the y-axis is the day when the samples were analyzed on the instrument. And so you see that this matches perfectly the day of the data collection. Now, it turned out that the first days was one cancer type, and the next day was another cancer type, and so on. Right? So that's not much that you can do with this experiment. So you need to randomize. Worse. So this is actually a paper which appeared in 2007, also kind of old, but this is a very famous example of this type of issue. So, and this is in the area of gene expression, not proteomics. So in 2007, researchers considered gene expression of Asians and people of European ancestry. And they found that 78% of genes are differentially expressed between Asians and Europeans. Okay? 78% of genes were differentially active, right, between Asians and Europeans. Okay, so what turned out was, and this is from the blog by Jeff Leake, who is a very well-known statistician who does this type of work with data. So his collaborators wanted to follow up on this, so he reanalyzed the data, didn't find anything wrong, so all the methods were just fine. 78% was there. But it was kind of weird. So this was a very old work. At that time, they used Affymetrix chips. And the actual chips, the cell files, they had a timestamp in the corner. And so they went all the way to the raw cell files to see the timestamp and to realize that there was 1 year difference between when they profiled Asian samples and the European samples. No wonder, right? Things are different. And these are probably true differences, but not for the reasons, right, that we think, right? They were due to difference, in time of data collection. So of course, this is not true. So we don't want to do this type of things. Okay, and this is also a famous quote from Fisher. So to call in the statistician after the experiment is done may be no more than asking him to perform a post-mortem examination. He may be able to say what the experiment died of. Okay, so now going back to your question and saying, okay, well, what happens if we have many days, right? And we have like all the kind of long-running experiments. And in particular, time, again, is a proxy for many things. We know that time has an impact on protein abundance. We cannot do much about this, but we know it's there. So in this case, there's a technique called blocking, which allows us to account for that. And blocking is a very effective technique which reduces both bias and variance and inefficiency. But this is also a technique which requires more statistical sophistication. So this is something. So randomizing and collecting replicates randomly, I think you can do it. You can just run like random number generator in Excel or in R, and it's fine. But blocking really requires us to understand what is the structure of variation in the entire kind of experimental setting. And this is how it looks. So remember, I was saying if we randomize different days, then we inflate our variation because now we have day-to-day variation as part of the variation within each group. So we have more variance in our samples. You can also see that now, let's say day 1 has the lowest abundance, day 2 has more abundance, and so on, right? So clearly, day has an impact on how what the intensities look like. So blocking is a technique which imposes a restriction on randomization, meaning we don't randomize completely, but we only randomize subsets of the samples. So here it means that on day 1, we choose to systematically allocate 1 healthy and 1 disease. Now, there's still randomization because we randomly select which healthy and randomly select which disease. And we would randomly allocate who goes first, who goes second, but we have 1 of each. Then on day 2, we do the same thing, another randomly selected healthy and randomly disease, and so on. And so clearly these pairs now, they are affected by the time, right, in which it works. But what we can do now, instead of comparing the mean of this group to the mean of this group, what we actually do, we look for differences within each pair.
How do you define is it affected by disease or by day?
Well, so what you do for that is you do a pilot study. Or, you look at your historical data from your lab, right? And you say, do I have day-to-day variation or not? And you can know this from in many ways. You can do it from QC samples and see how they vary across time, right? This type of technical things, you can know with enough experience, right? You would know that day-to-day variation, essentially, you try to measure the same thing in time, right? And see how much variance you have. So now, we assume that you know that this exists. You cannot control it. You cannot reduce it. But you know that day-to-day variation is there. So now you have an experiment where you try to compare healthy versus disease, and you know that you have day-to-day variation. So even if you randomize, well, first of all, this day-to-day variation will be part of the variance. But what can also happen, by the way, even randomly, you will have healthy in the beginning and disease in the end. Maybe not perfectly, but kind of randomly, this is not impossible, right? You can kind of have some, unequal allocation. What we do instead, we're saying, let us make sure that on day 1, I look at 1 healthy, 1 disease, or 2 healthy, 2 disease, or whatever you can do, right? But the same number. So in my cartoon here, I have 1 healthy, 1 disease. On day 2, I start over. I have 1 healthy, 1 disease, right? This is assuming that I know that I have day-to-day variation. So now, instead of comparing the mean of all the healthy to the mean of all disease, I will be focusing on the individual pairs. Now they're paired because they're on the same day. And I'm looking at the difference of the pair with day 1, look at the difference of the pair in day 2, day 3, and day 4, and I see that these differences all point to the same direction. They're always positive in this case, right? So disease is always higher than healthy. And so now your question will be, are these differences systematically positive, or are they fluctuating around 0, or are they systematically negative? So it has an effect of reducing your sample size, because instead of having 8 observations, you have now 4 differences. But these 4 differences, they're much more precise than the means of 8 data points. And so now, if you really have day-to-day variation, reducing this to 4 more precise numbers pays off. On the other hand, if you didn't have day-to-day variation, those lines, they will pretty much be on top of each other, right? Because all the days will be the same. So then you reduced your 8 observations to 4 pairs, but it wasn't necessary because you didn't really have a day-to-day variation. So what you need to do for this is several things. One is make sure you have your pilot study which establishes that you have a day-to-day variation. That's number one. The second, if you know you have, or whatever other source, right? Number two is you allocate your observations in a systematic way where you have a restriction on randomization. And number three, you need to analyze it accordingly. Because if you compare the means, well, you won't have the bias because now you ensure you have the same number of healthy and disease on every day, but you will be better off analyzing this as pairs as opposed to compare the means. So first you need to know that you have this artifact. Second, you allocate the sources like that. And third, you analyze it like that. And this is why I was saying earlier that we need to know how we analyze the data to calculate the sample size, because this type of choices will matter for the sample size in the end. So this is why we need to talk about this later. Yeah, go ahead.
In the case of identifying day-to-day variation, how many times should you do pairwise comparisons like that?
Oh, you don't. You can. The best way to understand that you have day-to-day variation is just to run some QC samples up front. And you run it just for several runs, and then just look at the variance, and you say, okay, how big the variance is, right? And you can compare this, with the variance that you would have from biological samples. Yeah. So this is something you do before you design the experiment, right? Or what you can also do, you can just look at your historical data and say, okay, what do we see from that? But QC samples will be a really good way.
If I didn't have day-to-day variation and I randomize it,
You just randomize.
no, but if I assumed I would have it, but I were wrong, I still, there's no harm in that, right?
There is a little bit, because you will be less sensitive. So because you reduced 8 data points to 4 differences. So now your analysis thinks you only have 4 data points. When you compare the means, your analysis thinks you have 8 data points, right? However, in this particular example, these 4 data points are much more precise. So your 4 data points have a lot more value than the original 8,
But
right?
I shouldn't do it if there is no reason.
Exactly. And this is, again, part of the experimental design. You can actually understand how much day-to-day variation you have, how much biological variation you have, and you can compare different strategies before collecting data for the actual experiment. So that's how we would usually do this in terms of deciding what's the optimal allocation.
But if I do it like that and I see that they're all on top of each other, I can still unpair them retrospectively.
You can, but usually it is much better to have your standard operating procedure before you see the data. Because you know what can also happen? Yeah, but my favorite protein looks really good if I don't unpair, right? It is very dangerous, right? So the right way to do it is to create your SOP before you start and follow it no matter what. However, you can use pilot studies to really decide what is the most common situation. Now, blocking, the only danger of blocking is that you just may be, in extreme cases, less sensitive. But in my view, it's a really minor risk. So you would be better off actually doing that.
So is one of the criteria to randomize in 4 days would be to run in 2 other days, run the healthy samples first, and 2 other days run
This will be worse, because now you have the two healthy day 1 to disease day 2. So now the difference between this, due to the disease, but also to the day.
But how are you going to make sure that the fact that disease will come out bigger than healthy is not because of the literal analysis?
So you randomize. So you randomize 2 things. You randomly select which subjects go on day 1. So 1 from healthy, 1 from disease. And you randomly randomize the order. So one day healthy goes first, the next day disease goes first. So you don't always go one after the other. That's very important, actually. Yeah, definitely. And by the way, I did 2 because I can draw a picture, but in real life you can do 5 and 5 or whatever your experiment allows.
Now, in this case, you know that the block variable is time or the days. How would you decide what are the block variables if mass spectrometry particulates.
Right.
To the experiment, how will you decide your time?
So time is a really good one. So if you have an experiment that runs over multiple days, I would say a day is a proxy for many things. Another is plates in which you process your samples. You have kind of natural block, and you make sure that each plate has representatives from every condition, and you randomly allocate them within the plate. And then the next plate that you start, it also has representatives from every condition. So there are many kind of natural things, but again, you can overdo it, right? So you don't want, because it's getting too complicated to analyze, and then there are other issues. So you really want to block only on the most important things, right? And you just completely randomize everything else. And if you feel like blocking becomes difficult, just randomize. So this would work fine.
You can only do pairwise blocking, or can you do?
Multiple. So yeah. So essentially, what it means that in a block you need to have equal number of representatives from each condition. So you can have 5 and 5. And in fact, I will show you in a minute. So let me just show you. Oh, okay. Let me show you some examples. So, and this is going back to your question about age and gender and so on. So just as before, we have two sources of variation. Therefore, we have two types of replicates, right? We have two types of randomization. Same thing here. We have two types of blocking. So blocking on biological risk factors. So here we have two populations. So they indeed have different characteristics: age, gender, weight, and whatnot. If we completely randomly select them from the population, we may end up with healthy all male and old, and disease all female and young. Just especially if the sample size is small, it can happen, right? So blocking will say, okay, I want to have from each group, I want to have one younger female, I want to have one older female, I want to have one younger male, and so on, right? So now you randomly select people subject to the specific characteristics that you prescribe. And as an example, this was a study we actually did with Munich Heart Center some years ago. They had a repository with plasma samples which were storing from all the patients who came to see them. So these were the numbers in the repository, stratified by age and gender. So one way to do this is to randomly sample from each line in this table, making sure that each line has the same number of replicates from each condition. So here we had 5 disease groups. Now, different lines can have different number of replicates, but within the line, you want to have the same number of replicates everywhere.
So sometimes you have obvious factor like gender or age, whatever. What about some not obvious parameter? It's pretty dozen of them, like stress or I don't know.
This is not easy. Again, you can overdo it easily, right? And every time you stratify, it kind of imposes, fine, especially eventually you'll have very few subjects in the population. So you'll be starting, overfitting to those particular subjects who are, female, older, but this disease and this medication, so you will end up with one person, right? And it becomes really difficult to have it representative. So I would only do it for the most important things. And again, randomization will take care of everything. If you feel that there will be many factors which can contribute, what this really means is that you need a larger sample size, right? So you stratify it only for the most important things and randomize everything else. And for also sample processing and labeling, this is another way of form of blocking. But I will probably stop here in the interest of time. So let me just finish here by saying that there's a lot of literature on that. I really like this Nature Methods points of significance vignettes. So it's a series of 2-page articles on very specific topics in statistics. And a lot of things that I will be using tomorrow and on Friday come from that, actually. And also in the schedule for our program, I posted a book which just appeared recently, which touches upon many of these issues. And it's a free online book. It is nice because it uses both kind of statistical methods and R. So it's very kind of appropriate for this class. And it has a paper version and a free online version as well. So yeah, so let me just finish here.